Okay, so we have today's speaker, Bartlomiej Czech here. He is going to tell us about something really exciting about what on which he has been working on this line. He has been working for many years, I guess. And so we are all excited to hear from him why the holographic dual of Riemann curvature should be a Berry curvature. So over to you, Bartek.
Okay, well, thank you very much. Thank you very much for the kind introduction and for the invitation to speak here. This work is mostly based on this paper from almost 2 years ago, so it's not super fresh work. I will tell you a little bit about the ongoing work in progress, which extends this in further directions. But today we will focus on this earlier work, which provides a basis for many other developments I will not have to tell you about now, which I'm working on currently. That paper was done in collaboration with Jan de Boer, Lampros Lampro, and Dongshang Ge. Dongshang is now a postdoc in Poland. Lampros is now a postdoc at UBC, and he was previously at MIT. And Jan de Boer, I think, needs no introductions from Amsterdam. So I should also say, I will say this in a moment, but let me say it here already, that I will not have a formula of the form Riemann curvature tensor at one location equals, but I will tell you why the Riemann curvature is related to a Berry curvature, and it will not be a qualitative, but a quantitative relation. So I think that the title is at least partly justified. Okay, so so the big question, this is a talk about the ADS-CFT correspondence, and we typically draw ADS as a solid cylinder and the CFT as a hollow cylinder. I anticipated that the audience would know enough about ADS-CFT, so it wouldn't be necessary to write like a metric of ADS and explain why we believe that ADS is related to a conformal field, or gravity in ADS is related to a conformal field theory. But for now, suffice it to say that we believe that there is a duality between these two objects. And for one thing, the isometric group of ADS is the conformal group in one fewer dimensions. So at least on the level of symmetries, these things really do match. Let me just say that. And the big question in holographic duality is how to see the ADS quantities, bulk quantities we call them, in the boundary CFT. So it's fine to say that ADS, gravity in ADS and conformal field theory are dual to each other, but we have to imagine a world in which we only knew the CFT and we didn't know about ADS, and we would somehow discover that an ADS description in one extra dimension in the solid cylinder rather than in a hollow cylinder, a description that contains gravity, how would we recognize it in the CFT if we didn't know about it from other means? That's a question about emergence, which is an interesting and important aspect of the ADS-CFT correspondence, and hopefully one that contains clues about deeper clues about any theory of quantum gravity. So that's why we like this question. How do I see ADS if I only know about CFT quantities? And it's really just a question about the dictionary between the two sides. If I have something well-defined in ADS, there should be a CFT object that computes it. Or if not, I wouldn't be able, or I shouldn't be drawing this two-sided arrow that says that the two things are equivalent or really properly dual. So that's the big question. How do I see ADS from a CFT? And a particular question today is, how do I see bulk Riemann curvature? So here's just a brief reminder of what it is. Consider some vector field, which I marked here as partial mu. And then I imagine applying parallel transport along a small rhombus of which is parametrized by, well, it's an infinitesimal rhombus whose sides point in some coordinate direction mu and rho. And then if I follow this rhombus and come back, then the question is, how did this vector field partial mu, how did it transform? And in general, it transforms as some kind of a matrix which acts on this mu index. And that matrix is going to, okay, so that's an object with two indices. And then I treat the nu and rho as two other indices, which have to be antisymmetric, because if they were symmetric, then this rhombus would have zero size, so there wouldn't be any transformation. And this object, which tells me about how such vector fields are transformed under such rhombus paths, is the Riemann tensor. So this is just a reminder of what it is. And the key thing is that we are going to take some object we know, for instance, a vector field that points in a particular coordinate direction, and we will see how it transforms when I take it around the loop. That's the kind of thing that we are interested in. And here I just repeat the disclaimer that I mentioned a moment ago, which is that I won't actually have a closed formula that says this R equals something, but we will get something very close to it and almost as satisfying. We will get an integral transform. So we'll take R mu nu, or R mu nu rho sigma, but integrate it along some surface in the bulk. And that's what an integral transform is. And that integral transform will be an integral transform of some components of R mu nu rho sigma, or partly, maybe some of these components are going to be contracted to the Ricci curvature. And then there will be some extra pieces. Those extra pieces are interesting and controllable, so you shouldn't be terribly skeptical about the fact that I say there will be some corrections, but there will also be some further corrections. So I'll give you a formula that involves R mu nu in some interesting and non-trivial way, and that integral transform that I will eventually tell you about will be related to the curvature of a certain Berry connection. Okay, so that's the goal for today. Now let me start with some basic facts about ADS CFT, which form the back. Yeah, question.
I'm sorry for interrupting.
Sure.
We are assuming the setup to be semi-classical, because in a complete theory of quantum gravity, maybe we do not have a well-defined notion of a Ricci scalar.
Yes. So yes. So I haven't been careful about things like that, but indeed, when we say that there is a space-time which is dual to a conformal field theory, we are automatic. I mean, just the moment we say that there is a space-time, that means that we're working in the large n limit of a CFT. And then there are always 1/n corrections when I take n to be large. So this holographic duality really requires that the conformal field theory have some large parameter, which we usually call n. When a CFT is a gauge theory, this would be like the number of colors in that gauge theory. And I'm only talking about the large n limit of the CFT, and that's the limit that gives rise to a semi-classical ADS space. But there are always 1/n corrections. And these quantities we're talking about are only defined at the level of the leading order and 1/n. There is in fact a further thing that I have to say to justify talking about these vector fields from a CFT point of view. At some point later, I haven't done this yet, but at some point later, we will have to be going back and forth between vector fields and objects in the conformal field theory. And in fact, that is only justified with one further assumption, and I will tell you about that assumption later, but right now there's not enough data to state the assumption, but I will state it later. It has to do with working in the so-called code subspace. Any other comments? Or yes, and I should have said this about large n from the beginning. So if there are no further comments, but I should say, please interrupt me with questions. I will be very happy to have questions. That will make my job far easier. Let me just summarize some basic facts about holographic duality, which will be necessary for me to get off the ground. And so here I drew again ADS space and CFT, this pair of cylinders, one solid, one hollow. The vertical direction in the direction of the cylinder means time. And that means that if I draw a time slice of the hollow cylinder, this is a Cauchy slice of the CFT. So this is where the Hilbert space of the CFT lives. And I will imagine that there is, so every ADS, asymptotically ADS geometry can arise from some set, maybe not a unique set because of 1/n corrections and such things, but from some set of states in the CFT, and I will assume that the state that produces this semi-classical geometry is a pure state. And I will further assume, which is not really a justified assumption, but I will just go ahead and be cavalier and assume that this Hilbert space factorizes into a product over divisions of the Cauchy slice into two pieces. In other words, the physics in A is independent from the physics of the complement of the region A, which I call A bar. Now, when the CFT is a gauge theory, this assumption is not justified, but all the things that I will tell you about can be stated without this assumption, but it's just a very it's just a very tedious process to write down all the technically correct statements. So for the purpose of presentation, I will be assuming that the Hilbert space factorizes like this, but you should remember throughout my talk that, first of all, that assumption does not in fact hold in real life, but on the other hand, that things I say can be upgraded to the rigors of real life. And so we can actually remove this assumption if and when it's necessary. So this assumption is just for presentation purposes. Okay. But basically this says that this assumption says that the physics in A and physics in the complement of the region A can be meaningfully separated and independent, made independent. In that context, we should think of A as being our lab. This is where we do our experiments. And in practice, what this means is that we will only be working in A with observables of the form some observable in A tensor the identity on A bar. That's the kind of observable that we will be using throughout the talk to do physics. The failure of this assumption is the statement that there are in fact no good observables of this form. And so any observable is necessarily delocalized. That is true, especially in gauge theories, but we will not. We will just go ahead and assume that, in fact, it does make sense to talk about such observables. Okay, so when I work with this type of observables that act non-trivially only in the region A, but not in A bar, then let's consider some expectation value in this state psi of that observable. Well, here I write it as an expectation value in the state psi. Now I go to the trace, so I just rearrange the order in this expression. But because I have an identity on A bar, that means I can do this trace whenever there's a Hilbert space factorization, this is justified. I can do it in two steps, first on over A bar and then over A. And so this is this line of the derivation. And now the object that is boxed here is an object that is ready to be put in a trace over the Hilbert space A. We call this guy rho sub A, and we call it the reduced density matrix of the region A. So this is a definition of a reduced density matrix of A. This is an object in quantum mechanics, or in this case in quantum field theory, that knows all and only about what happens in region A and is completely oblivious to what happens in the region A bar. Now, it turns out to be very useful to write rho as an exponential of minus some other object, and this other object is called the modular Hamiltonian. And it's these modular Hamiltonians, the variation of them, that's going to eventually give rise to a Berry phase that will be the subject of this talk. Are there any questions? Are there any questions at this point?
Yeah, probably you're going to say about this later, but this modular Hamiltonian is not generically something local, right? It's not something that you can write as a integral of some density.
Correct. So the modular Hamiltonian is generally a big mess, but it does have a nearly local action in the a small neighborhood of what's called the Ryutakainagi surface, and I will say this in a moment. And that's the only thing that we will be. That's the only region where we'll be using the modular Hamiltonian. So in fact, we will be able to get away with assuming that it does act locally in the bulk. Not in the boundary, but in the bulk. But we'll talk about this in a moment. But indeed, in general, the modular Hamiltonian is not a local object, so it's pretty tough to study. So here I actually copied the same slide, but added some more stuff. So we got to this point and defined the modular Hamiltonian. There's one other useful quantity, which is called the entanglement entropy. That's just the von Neumann entropy of this reduced density matrix rho sub A. And it's a number eventually. And this number tells me how the region A is entangled with A bar. So we have these three things: the density matrix, the modular Hamiltonian, which is minus log of the density matrix, and the entanglement entropy, which is the von Neumann entropy of this rho A. And the question that we should be asking is, these are objects in the CFT. What are they on the ADS side? And so here is an ADS side of the picture. And I drew all the objects and color-coded them as they are color-coded here. So the density matrix is green, the modular Hamiltonian is orange, if you can tell, and the entanglement entropy is red. So let's see how they look like on this picture. Here's the green. Picture that I will be using. So the first question in interpreting these CFT quantities, rho, h, and s, on the bulk side is, what is rho in the bulk? Or maybe I should explain this question a little bit more. So I mentioned that the density matrix captures all the information about our system if I am reduced to just some region A and I have no access to some A bar. The prototypical situation like that is when I do experiments in some lab A, and A bar is just the rest of the universe. And so rho A knows everything about what I can do within the confines of my laboratory called A. Now imagine that I divided the CFT into two pieces. This is A and this is A bar. But this CFT gives rise to a holographic spacetime. So a question that we can ask is, if I only know about what happens in my CFT lab called A, then how much of the ADS spacetime can I recover from this? By Almeri, Dong, and Harlow, I think in 2015. But in fact, it goes back, it was conjectured, I was happy to be part of this collaboration by myself and Jana Karczmarek and Fernando Nogueira and Mark van Ramsdonk. We conjectured, and those guys then proved that the bulk dual of the density matrix is this region called the entanglement wedge. And so I should tell you about what the entanglement wedge is. It is the bulk domain of dependence of a space-like region which separates the boundary region A from a minimal surface anchored on A. So here is a region A, and I'm asking, what is a minimal surface that passes through the bulk, which connects the ends of this A? Once I find it, I find some region, I find some Cauchy slice that passes through A and through this minimal surface. I take the region in between and I ask, what is the region in space-time which is only, which is not time-like separated from any region on the complement of this string? This is what's called the domain of dependence. The point of a domain of dependence of this concept is, this is a region without needing to know what happens on the complement of a spatial slice of the spacetime. So I've divided the spacetime into two pieces. One sits between a minimal surface and the region A. The other one obviously sits on the complement, so between the minimal surface and the region A bar. And then I'm asking, what is the part of spacetime that where I can tell what's going on without needing any data outside of this region in between A and the minimal surface? This is called or these people have proven is the region which is the bulk dual of the reduced density matrix of A. Okay. Are there any questions about what the entanglement wedge is? I have drawn it here. There's a region A, there's a minimal surface, and there is some domain of dependence of the space-like region sitting between them. That's the entanglement wedge.
Yeah,
Any questions or comments?
Not a question, it's just that your internet is disconnecting for a little while, so we are losing a few words in between, but since you're repeating that, we're getting it, but it's just, yeah.
Okay.
Yeah. So
Well,
it's
that's
not,
not good, but I'm not sure. This right now, but let's keep going, and then if the problem persists, then maybe we can switch networks. But okay. So are you hearing what I'm saying right now?
Yeah. But just a while ago, I lost a few words again, but you're coming back.
Okay.
It's only a very brief time that we lose you, but
hopefully this will solve itself. Okay. So clearly in the definition of the entanglement wedge, this minimal surface is a very important concept. We call it also the Ryutakainagi surface. In fact, technically, it is not a minimal, but an extremal surface. So I minimize it over a spatial slice, but then I have to maximize it over different spatial slices that I have here. This is called the maximum construction of the RT surface. I've been writing minimal surface, but technically I should be saying the maximum surface. And this surface, it has an area. And when I take the area in Planck units, in fact, it equals this number, which is the entanglement entropy of the region A. This was first conjectured by Ryutakainagi in 2006, and this really gave rise to this whole development about information theory informing ADS-CFT. And then HA, this is the last piece of this dictionary which we haven't explained yet. So HA is an operator which generates boosts, or, well, so first of all, when I work in the large N limit, and further, when I work in the so-called code subspace of the CFT, this is the space which has a bulk interpretation in terms of low energy effective field theory, then this HA can be thought of as a vector field which generates boosts which are orthogonal to the RT surface. And so HA really generates these. This is an orbit of HA. It can be represented as a vector field orthogonal to this region. Now, Ian said, but isn't it true that HA is non-local? It sounds like it's local. And so this description as a vector field breaks down when I go further away from the RT surface. But when I remain close enough to the RT surface, this is in fact a good description. This was discussed by Aitor Lewkowicz and Tom Faulkner in a paper of theirs, I think in 2018. And so because we will only be really working or applying this formalism only in the neighborhood of the extremal surface, therefore I will not worry about these corrections. But you should remember that every statement I make is actually subject to corrections which become large when I go far away enough from the RT surface. But I won't be going far enough from the RT surface.
Sorry, I have a very basic question. So you're saying this, so if it operates on an operator in this sense, I think what e to the power HA, some operator in the bulk times e to the power HA, that will basically translate the operator on this boost curve. But then you have to also pull this bulk operator to the boundary somehow, right? And that is the standard kind of way that you propose.
Well, that's taking the operator to the by taking the operator to the boundary. Do you mean writing the bulk operator as a combination of boundary operators?
Or
do you mean? Oh, okay, yeah. This is the so-called HKLL construction, and yeah. So you can do it, and in fact, the most modern way of doing this, which is so there was an old way of doing HKLL, which was suited for spacetimes like ADS-Rindler space that have a certain simplifying property. But then that simpler method didn't apply in cases where the simplifying property does not hold. So there is a modern way of doing HKLL, which gets around this problem. And that modern way, in fact, exploits the very thing that you said, which is it starts from the idea that whatever these operators are, they have to get moved around by the modular Hamiltonian as you, well, yes, when you conjugate it by well, when you apply what's called modular flow, basically when you flow with this HA. And so what you just said is in fact the key to making a better version of HKLL, which is the more modern HKLL. That's also due to Tom Faulkner and Aitor Levkovich, as far as I can tell.
Yeah, can I ask again that then what is why we should believe this? Because that this thing should be true, that the modular Hamiltonian should generate these flows in the bulk?
Well, a qualitative statement about this is that this it is something that doesn't change with the RT surface. It also always exists.
We just lost you, whatever you said.
Oh,
ask the questions.
Oh, okay.
Okay.
But so I'll say again. So a qualitative argument that makes it believable is that this flow that generates a boost keeps the RT surface fixed. It doesn't move it around. And so it's consistent, at least, with the fact that that e to the minus h, which is rho, is the entire entanglement wedge. So the entanglement wedge is not moving anywhere. Like if this h didn't preserve the RT surface, then applying h would basically take the boundary of the entanglement wedge and push it someplace else. But that means that the entanglement wedge wouldn't be preserved. And so this is a very basic sort of bottom line sanity check that it makes sense. And a further sanity check is that this is something that exists for every RT surface, so for every entanglement wedge. In higher dimensions, this is actually a constraining thing. In 2+1 bulk dimensions, there's always something that just flows orthogonally to the RT surface, and that's not that interesting. But in higher dimensions, these minimal surfaces, these extremal surfaces have shape because the boundary region can have different shapes. And also because the extremality condition means that the trace of the extrinsic curvature tensor of the surface has to vanish, but it means that just that it exists is also a strong hint. But the full arguments in favor of this were given by JLMS, Jafaris, Su, Maldacena, and Aitor Levkovich, and that's a much more serious argument that I will not get into. Okay.
Yeah, thanks.
Sure. So, okay, so these are the dictionary entries that we will need. There's an entanglement wedge, there's a flow, which is H, and there is the minimal surface, which is the von Neumann entropy of rho. Okay. And so this is summarized here. And in fact, so it's really important to recognize that this HA, in fact, generates a symmetry of the entanglement wedge. Now, when I say the entanglement wedge is dual to rho A, it's obvious that rho A commutes with HA. So at that level, it's a trivial statement that the modular Hamiltonian generates a symmetry of rho A. But it's a far less trivial statement when I apply it to the expectation value of some observable. So here's the expectation value of some observable, which I call rho A. And because rho A commutes with HA, therefore I can just insert some of these exponentials of HA. But then by the cyclicity of trace, I can recognize that this is also equal to trace rho A times a modular flowed version of my original operator OA, of my original observable. So this equality means that the observable rho A and the modular Hamiltonian flowed version of rho A, which is this thing, are on a completely equal footing so long as they are used inside rho sub A. Which means that within rho sub A, or within the entanglement wedge of A, rho A and the modular flowed version of itself are related by a symmetry, and that symmetry is modular flow. So this is what I said here. Therefore, these observables are indistinguishable in the entanglement wedge of A, because the entanglement wedge is what I get from rho A. If they're indistinguishable by using rho A in the field theory, that means that they must be indistinguishable from the bulk point of view inside this entanglement wedge. Even though they are different observables, they are indistinguishable within the context of this entanglement wedge of A. They are distinguishable in other states. So when I use them inside some rho, which is not equal to rho A, then they would be different observables. But if I just do my experiments in rho A, then those observables are related by a symmetry. So this is an interesting kind of.
A little bit. Sorry to interrupt, but this OA is an point is an operator in the bulk or in the boundary in this argument that you just gave.
We can think of this as a bulk operator. So by using HKLL, I'm really kind of thinking interchangeably between OA as a CFT observable and a bulk version of OA. The only thing I need here is the statement that OA is really OA, as in it only acts in the region A, it doesn't act in the complement. So the fact that it doesn't act in the complement means that it represents some observable in the bulk as well by applying the HKLL dictionary. That observable may not be local, but it doesn't matter. Anyway, any observable A which acts in a localized fashion in A is related to a modular flowed version of itself by a symmetry.
So you're also assuming locality in the bulk, that there would be a local description in the bulk so that you could localize observables of the entanglement wedge.
In this statement, I am not assuming this, because even if the observable OA is not local, let me write it as some very multi-local observable in the bulk. So not a 1-point or not a 2-point function, but an n-point observable where n is arbitrarily large. And then I will just apply this modular flow. I will get some other observable, and that other observable is, like I said, on an equal footing with the original OA, but I didn't have to assume that OA was local at any point.
I see. So
I might as well just take some OA, which is not a local observable from the bulk point of view, apply modular flow to it. That modular flow itself may not be local. If I were far away from the RT surface, then it's generically not local. And so I'm making a statement about an equivalence between two different non-local objects.
As far as experiments in the region A go.
As far as experiments, yes. But then you could take these observables and use them in some other state, and they would be very different. Mm-hmm. So it's an accident of that state that they become indistinguishable.
Okay.
So if we label observables to actually distinguish them, then the physics in rho A is independent of that labeling. And so we view the labeling as a gauge symmetry. And so this is something that will be important in the rest of the talk, that these observables are different. They are different in the full theory, but in the context of a single state, the difference between them is arbitrary. So in that context, we may view this as a gauge symmetry. So the next question is, how is this gauge symmetry manifested in the bulk? And of course, the answer is we have to flow by HA, which if I'm close enough to the RT surface is just going to apply boosts which are orthogonal to the RT surface, but farther away it will do something more non-trivial. But let's focus on what happens near the RT surface. So what is this symmetry? I will take in fact, we don't have to just use the boost, which is generated by HA. We can take any vector field that commutes with the orthogonal boost, because if it commutes with the boost, that means that it represents some operator which commutes with the modular Hamiltonian of HA. But the modular Hamiltonian determines the entire density matrix, so it determines everything in the entanglement wedge. It determines the entire rho A. So in fact, any vector field that commutes with these orthogonal boost also generates a symmetry by the same argument that we just mentioned before. Okay. So here's what I made the same statement I make the same statement here again. Suppose that there is some symmetry P which commutes with HA, then I can write the same argument I mentioned before, time evolve, modular time evolve with respect to a new operator called P, and such P evolved operators are equivalent to the original O within the context of this entanglement wedge rho A, or this density matrix rho A. And so P also generates a symmetry. So anything that commutes with the boost vector field is going to at any vector field.
Sorry, we lost you after you said anything that commutes with the boost, and we lost you for like a few seconds.
Oh dear. So I was just okay, but I think I was making the exact point that I was making seconds before, which is that any vector field that commutes with the RT surface generates a symmetry of a gauge symmetry in the same sense that I said in the previous slide. Okay. So what is the orbit, the total orbit of this gauge symmetry? How can we view this entire gauge symmetry? And so the answer is that to see how the different gauges work, we just have to apply various vector fields that commute with H. That means H itself, but also any other vector fields that do it. Of the RT surface. And so here I chose it. With red ticks, I'm imposing some longitudinal coordinate system along the RT surface. And these arrows represent some directions orthogonal to the RT surface. And then these directions and the ticks may change under the application of P and under the application of H mod. And so the gauge orbit of our gauge symmetry is really the set of all possible coordinate systems that I can set in a closed neighborhood of the RT surface. And so that's the punchline of this part of the talk, that coordinate systems near the RT surface span a gauge orbit of this gauge symmetry I discussed. Any questions at this point?
Yeah, so because I lost you again for a bit, can I say that this gauge symmetry is then the set of diffeomorphisms that leave the RT surface invariant, or is that
yes, you can say that's right. This the orbit of this gauge symmetry is the set of diffeomorphisms that keep this RT surface invariant.
Okay.
I'm going to try.
Yeah, since we are losing you from time to time, it's could you repeat the argument of why it's a gauge symmetry? That part was not really altogether clear.
I think I'm going to try connecting with a different network. Why don't you just give me a minute or two, and then
sure.
I will. Okay.
Yeah, sure.
I'll be right back.
Sure. Okay, that's worthwhile.
In the meantime, if anybody in the audience understood why it's a gauge symmetry, maybe a different perspective will help.
Yeah, I think the point is that if you take trace rho A of any observable and you take anything that commutes with HA, the modular Hamiltonian, so it will give you the same physical result. So if you do some, so essentially P can be thought of as generating some gauge transformation, because it leaves.
But why gauge transformation is not clear to me. If you have a symmetry, then even global symmetries, if you do a transformation, will give you the same result, right? So what is the key argument that tells you that this is a gauge symmetry and not a global symmetry?
Good point. Yeah. I think the point, of course, is a local. Usually, if you say that it is a local operator, if it acts, I don't know actually. So if you, I don't know whether you can localize it, or if it depends on. It's a good point.
I don't know if you, even if you have local, I don't see why. I didn't just follow why it is identified as a gauge symmetry. The OA doesn't seem to, whether OA is a local operator or not, did that make a difference in this context?
Yeah, I think the point could be that this P can be, you can then multiply P with some kind of support function that depends, that you could choose the support to be arbitrarily small, so you can promote it to something like a local symmetry also. So it is, the point is that it should commute with this bulk Hamiltonian. So probably, so you could localize this action of P probably, but probably it's better if he answers it.
Yeah, I think so, because in case of gauge symmetries, normally you don't write it in terms of a commutation with the commutator with the Hamiltonian vanishing, right? Those are in terms of generators of global symmetries that one writes such commutation relations, right? Gauge symmetries are kind of redundancies for which you don't even need to write this kind of
still the
statement.
charges, the global charges are conserved, right?
Yeah, global charges are conserved, but they're related to part of the global transform, the global part of the gauge symmetry, right? It's not really.
Yeah, but you could probably act with the compact support of this charge, and that generates the gauge transformation too, and that's the idea, I guess.
Hi, can you?
You're back, so
I'm back, and sorry for this taking a while. Can you hear me now better?
Yeah, it looks smoother, but only time will tell whether this is working.
Only time will tell, indeed. And let me start. I have to share screen again. So can we see the screen again? Okay. Yeah. So I apologize for this on my end. Sorry about that.
It's not your fault. So Debashis has a question for you, actually.
Please.
Yeah, I already asked you that. Could you go through the argument of why you identify this as a gauge symmetry as opposed to a global symmetry?
It's I say it's a gauge symmetry because the physics is independent, because it's a symmetry of our description, but not of the actual physics. So we may choose some labels to distinguish this rho A from the modular flowed version of rho A.
You mean OA, not rho A. Rho A was anyway.
Sorry, that's right. OA. Yeah, we can choose to call OA, and we can choose this one to be a modular flowed version of OA. But then I could have started with this being OA, and this would be some other modular flowed version of that guy. And there is no way to prefer this one over that one as the observable at modular time.
Okay, so that is the redundancy in the description. That's the gauge symmetry, I see.
That's right, yeah.
So, and that's true for any of the operators that you can write, any operator that you write in this.
Yeah, it's true for any operator, yeah. And this is really a trivial statement. It's a statement that if I'm making if I am using a symmetric object, because I will be using these rows to compute expectation, these O's, sorry, to compute expectation value in trace rho. If rho is symmetric under something, say HA,
that part I understood. Yeah.
Then any asymmetry in OA drops out of this expression, and that's the statement I make.
Yeah. So again, sorry, just to follow up. Sorry for the interruption. Sure. Just to follow up, and you went further and identified this class of family of operators PA, and from which you're going to identify this as a diffeomorphism. Yeah. So how do you identify the full set of diffeomorphism? Is there some?
Yeah, so there is a larger set of diffeomorphisms in the full CFT, but when we're just working in the 1 over n leading order and 1 over n, and when we're working in the so-called code subspace that I didn't say much about, but that's a necessary assumption as well, then we can represent these things geometrically in the bulk. And when I represent these things geometrically in the bulk, then I ask, well, what is this gauge symmetry? Well, it's a symmetry of description of a small neighborhood of the RT surface. So what are these symmetries of description? They are different coordinate systems that I can choose in the neighborhood of the surface.
But didn't have a condition that these vector fields have to be orthogonal to the Ryutakainagi surface there? Then what about the vector fields which are on the Cauchy slice? How do you get those?
These are vector fields that have to preserve the RT surface. So these the symmetries are generated by things that, I think I have it here, by things that commute with the modular Hamiltonian. Commuting with the modular Hamiltonian is equivalent to preserving the RT surface. And so the symmetry is comprised or is generated by vector fields that preserve the RT surface. Now, how would I detect the effect of such a symmetry? Well, the RT surface itself doesn't detect it, but if I choose some coordinates on the RT surface, then this coordinate system would get affected. And so that's the reason why the symmetry corresponds to the different coordinate systems I can choose on the RT surface. And the kind of did I answer your question or no, Debashis?
Yeah, well, for the moment, I'm good. Thanks.
Oh, okay. So, I mean, maybe I can stay behind after the talk and continue discussing this. But for now, let's just assume.
One thing I wanted also to get clarification. So the P cannot be localized, is it? So I was having the impression that you could make a small diffeomorphism in a neighborhood of this RT surface, which can preserve it. But is P, so that is why I thought you were calling it global. But a gauge symmetry as opposed to a global symmetry. But
when I use the phrase gauge symmetry, it is not. I think we are conflating two usages of the word gauge. It's frequent when we discuss gravity to equate the word gauge with diffeomorphism, so long as it's a small diffeomorphism. But that's not what I mean here. I mean gauge in the sense of labeling observables in the entanglement wedge such that differently labeled observables have the same expectation values. Now, that's the kind of gauge I'm talking about. Yeah, this is a smaller set of gauges than all diffeomorphisms, because general diffeomorphisms are going to move my RT surface around, and I don't want that.
So P is a finite set of diffeom independence. P is a finite set typically. That's why. It
probably is not going to be a finite set, because if the entanglement, let's see. Well, no, it's definitely not a finite set, because if I take an RT surface, then I can stretch it and contract it without, well, basically I can do a diffeomorphism that preserves the RT surface, and there are definitely infinitely many of those.
Yeah, that's
why the surface itself can get stretched and contract between points while the surface itself is being preserved. And so we would detect this by putting some ticks here and then checking if the ticks are the same distance or different distances from each other after the symmetry. So these are these kind of longitudinal vector fields. These would be P's. Another thing that generates the symmetry is the H itself. This acts orthogonally in the boost direction. So that means that I could have some arrows that choose orthogonal directions to my RT surface, and those arrows could get boosted this way or that way, if you can see what I'm doing with my fingers. So these are the kinds of things that comprise this symmetry.
Okay, thanks for the clarification.
Great. So if I now follow, so the next thing that we will want to do is we would follow a loop in the space of regions. And the space of regions is called kinematic space. This is a phrase that my collaborators and I have coined over the years. And so imagine that I follow a loop in the space of regions. Namely, I start with one region. That region has some coordinate system that's in the neighborhood of its RT surface. Then I go to a different region, and I come back to where I started. That's a closed loop in the space of regions. Each of the regions I visited along the way defines for me some coordinate system. And then I will ask, is the coordinate system I ended up with the same as the coordinate system that I started with? I just want to highlight that this kind of question, that's the question I'm posing now, is really very closely analogous to our construction of the Riemann tensor. Yes, I had some vector field locally, which basically chooses a direction away from a certain point. Then I follow a loop, and then I ask what happened with that particular vector field. So when we talk about the Riemann curvature tensor, we are choosing a local set of coordinates around a single point Then we follow a loop, and then we ask how that coordinate system changed. Did the mu direction go into some other combination of the original directions? Now, what the question I'm posing here is really the same kind of question, except my coordinate system is not fixed is not just applied at a particular point. That was the case for the Riemann curvature tensor, but for the entire RT surface, for the entire extremal surface. So the kind of loop that we get, it's not this loop identically. The kind of picture we get is this picture. I start from some RT surface. It has some local coordinate system, which is given by the direction, by the distances between neighboring arrows. And these arrows are supposed to be orthogonal with respect to the orthogonal Minkowski metric. And then I'm going to take this, let's say this black coordinate system, and go to the blue one, and then go to the top, go to the red one, and go to the top. And the difference between them corresponds to a closed loop. And then I'm asking, after making a closed loop, did I come back to the same kind of coordinate system or different? And you see the blue arrows are different from the red arrows. So that means that I incurred some honest curvature. And that curvature is a surface-wise analog of the picture we have here, which defines the Riemann curvature tensor. Does that make sense or not, what we're doing?
Yeah, just not so, I just have a bit confused. So you said that you are doing some loop in the space of regions that is equivalent to taking a loop in the space of RT surfaces?
Mm-hmm.
And you're saying,
region. Because every region has some RT surface for it. So yes, so a closed loop in the space of regions is a loop in the space of RT surface.
Okay, now I understand. So basically, when you come back to it, you will not end up with the same coordinate system, but this is a sort of infinite dimensional description.
Yeah. So it's a surface-wise version of this picture. And so that's the reason why I say that the curvature I'm talking about is like the Riemann curvature. In fact, when you compute it, it turns out to be an object constructed from these guys, but it's not identically that guy. Okay.
Just to be clear, I mean, is it more natural to think of this curvature as having two curved indices and two local tangent space indices, more like RAB mu nu, if we use some standard notation? Because you're using the local coordinate system, right? You start with a vector field del mu. So that vector field mu index has to contract with some, give you a new index. But the other two indices are movement in the local frame. So that would be some local tangent frame indices. Is that more natural?
Yes, yeah, excellent. That's a very good point, and you're completely right. So basically what you're saying is that when I'm moving points around, it's fine for this mu and rho and this mu to be on an equal footing. But when I'm using entire surfaces, then this is a direction in the space of surfaces. This is a direction in space-time, and so they are not the same kind of indices. I think that's the point you're making, and I completely agree. That's right.
Yeah, thanks.
Mm-hmm. Okay, so, but I think I managed to convey the kind of question that we will be asking for. And I think maybe I managed to convince you that the answer eventually is going to be an integral transform of some components of this R, because we're basically doing this job, except we're doing it surface by surface. But there is one more thing, but that one more thing is the most important maybe, is that I haven't told you how to actually move these coordinate systems from place to place. So in the case of Riemannian geometry, we know what we mean by this transport. Yes, there is a notion of parallel transport, which is given by let's say the Levi-Civita connection, or maybe some other connection you're using, and that's the guy from which you would construct R. But what is the notion of a connection that allows us to move the various coordinate systems from place to place in the present case? And so what does it mean to follow a loop? So I have to give you a rule for how to, or a set of rules for how to take one of these coordinate systems, or equivalently a set of labels on the observables in the Hilbert space of A. And then I have to be able to transport this coordinate system, or these labels. And that transport, a rule for this transport is called a connection. So I have to specify a connection on kinematic space. That is a connection on the space of regions. And in order to really say that we have reconstructed it from the boundary point of view, that connection has to be stated entirely in the language of the boundary CFT. In other words, if I give you a rule, but that rule uses the bulk, then okay, it's just a description, but it's not explaining to me how ideas came from the CFT. So I have to give you some set of rules and phrase those rules entirely in a CFT language. And so I'll give you a connection now, and I will argue that that connection is in fact a generalization. It's not identically that, but it's a generalization of the Berry connection. And so that's the plan for the remaining. I should have 2 minutes of the talk. So I don't know how I'm going to do it, but that would be the plan.
Well, you have
talk.
easily 6 minutes, and you can take more time, no problem, because we have started at 34. You have easily 6 minutes, and because we also lost time, you can easily take 15 more minutes, no problem. Yeah.
15. I'll try to finish in 15. Thank you so much, and sorry for being late. Okay, so what's the Berry connection? Let's take a time-dependent here's a brief reminder. Let's take a time-dependent Hamiltonian, H, which depends on time, but let's say that it depends on some set of on some parameter lambda, which in turn depends on time. So lambda is some set of parameters that specify H, the Hamiltonian. And so this is a complete change of settings from before, and we're going to tie it up together in a moment. And this is just a reminder of what the Berry connection is. Now let's start up the system in its ground state. And for simplicity, let's imagine that the ground state has energy 0. So I can always do this by adding a constant to the Hamiltonian. Now, if this time-varying Hamiltonian varies slowly enough, then the system will always remain in its ground state. This is the content of the Adiabatic theorem. And I'm going to impose this condition at all future times as well. In other words, I will just assume that H acting on the ground state is always equal to 0 by appropriately shifting the Hamiltonians I encounter all the way by an appropriate constant. I can always do that. Now, let's pick some bases of ground states. Let's call them psi of lambda. So if you give me H of lambda, I'm going to say psi of lambda is a ground state. This is this statement here. But these psi's of lambda are ambiguous by a phase, because I could have chosen minus psi of lambda or e to the I pi over 2 times psi of lambda, and these would be equally good ground states. And so the question is, how do I represent a physical state in terms of these this arbitrary basis of ground states which are ambiguous by a phase? Well, whatever they are, they have to be related to the ground states. The state at a given time has to be related to the ground state of the Hamiltonian at that time, which is psi of lambda of t. It has to be related by a phase. So I can write this kind of ansatz for the state. So let me just explain the ansatz. Phi is the actual state at hand. Psi is some basis I chose for the ground state, which is ambiguous by a phase. And now we need to find the phase. That phase, you might say, is unphysical on its own, but we can take 2 copies of the same state, pass one of them through this changing Hamiltonian. The other one maybe nothing happens to it. I'm just going to keep the system, that other copy, separate from the other one. Here, the Hamiltonian is not changing at all. In fact, the Hamiltonian has value 0 when it acts on it, so literally nothing happens to that state. And then I would interfere them at the end of the day. So that interference would be taking an inner product of psi of lambda of t with the original psi of lambda of 0, and that's exactly that phase. So in fact, the phase is measurable if I have 2 copies of the state. One of them I do nothing with, the other one I pass through this time-dependent Hamiltonian. Notice that to extract this phase, I have to get a loop, yes? There must be a loop drawn. Here I have time and the space lambda, the space of parameters. I have to follow some kind of loop to extract this phase. And so there is some sense that the loop might be a little similar to the loop in the space of regions we talked about. In fact, that will happen, but I'll tell you about how in a moment. Okay, so how do we find this gamma? We want to find this gamma, the phase. This is the Berry phase. How do we find it? Well, we have an ansatz for the state. Here is the ansatz. So we can plug this ansatz into the Schrödinger equation. And remember, H acting on psi equals 0, but it also is equal to it generates a time evolution of psi. So I can apply ddt to the state that I have, including its ansatz. And then I get 2 terms, one from the variation of the phase and one from the variation of the state itself, because H of lambda depends on lambda. Sorry, because psi of lambda depends on lambda, because I have different ground states, different values of lambda. When I now take an inner product with psi of lambda, then I get an equation of this type. And this is the equation for the Berry phase. So maybe it's nicer to write gamma dot as minus I times the inner product of psi and psi dot. This thing is called the Berry connection. Oh, I should maybe say that this object is always, this gamma dot is always real. Why is it real? Well, here's a little calculation. I took psi dot and I took a derivative of it, and I recognized that when I take a derivative of 1, these are the states of normal, this state is normalized, I can write it in this form. This vanishes, but it's also given by 2 times the real part of psi dot. So psi dot has no real part, it's purely imaginary. When I multiply it by minus I will get a real phase. And so gamma is really real. That's good news. Now, so when I want to compute gamma, I need to take an integral of this thing. So I wrote the integral out explicitly here. Here I wrote it in terms of d lambda and psi dot. I could just even forget about d lambda and go to a completely coordinate-free notation, which will be psi taken inner product with d psi. This is the kind of integral that computes that phase. The integrand here, well, integrals are always maps from forms to numbers. So the integrand here is a 1 form, and this 1 form we call the Berry connection, just like a connection in GR is also a 1 form. So this thing we call a Berry connection, and it gives us it attaches a very specific phase to the state phi, and that specific phase is an entirely geometric object. It doesn't depend on how fast or how slow I move through the space of parameters, so long as it is slow enough so that the adiabatic theorem applies. And it really just depends on how my Hamiltonian varied with the space of parameters. So it's a geometric phase which captures the variations of the Hamiltonian more than any dynamical property of the system. It's different from the dynamical phase, in other words. So I wrote the state phi at all times in this final form. Here I substituted the form of the Berry phase, which we computed in the previous box. And maybe at this point I should pause and ask, are there any questions about this super brief review of what the Berry phase and what the Berry connection are? Okay. I assume that there are no questions if I'm not hearing them. Okay, but the salient features of this very brief presentation are that because the system was subjected to time-dependent Hamiltonians, an additional phase showed up in the state. This phase can be extracted by interference experiments which are related to a loop in the space of parameters. This is this loop that I have written down here over lambda. So I have to take a closed loop in the space of parameters to extract the phase. And really, this is just, we compute this phase just by applying the Schrödinger equation. So it's just applying known rules of physics necessitate that such a phase must arise. And it only depends on an integral that happens in the space of lambda. So it's entirely derived from the geometric features of how I actually varied my Hamiltonian with this parameter lambda. These are the key features of this calculation. Any questions or comments at this point? Okay, so this is our final answer for what the state is, including the Berry phase. Now, what's important to me, and the shortest route to understand why this is related to what we said before, is to take an infinitesimal change of this expression as I vary the state from t to, let's say, t plus dt. Okay, so I'm taking an infinitesimal change of the state phi, which I computed. And here is a little calculation. You can go through the calculation in detail. First of all, there are 2 things that can that give rise to a variation in the state phi. This psi here can change, and that's this term, or the integral, the exponential here might change. And that gives rise, in fact, to this term, which if you look at it for a moment, you will recognize that that's true. And so the variation in the state phi, this d phi, is given by d phi itself. So is given by d psi itself. This is the change in my favorite bases that I chose ahead of time. But then in front of it acts a projector, which projects me onto a space which is orthogonal to my current state. So this, I think, is the most interesting way of stating what the Berry phase is about. If you choose your phase wrong for the state, as the state undergoes this time-dependent Hamiltonian evolution, then sometimes, if you choose the phase wrong, then generically, actually, not sometimes, the time dependence in your state is not going to be orthogonal to the state itself. If you choose the Berry phase, then your state always varies in a direction which is orthogonal to the state. This projector here, which I've just computed, ensures that. If I had any other phase here, not the Berry phase, then this projector here would get screwed up, and then the variation would not be orthogonal to the state itself. But choosing a Berry phase is like saying, after this phase, which is the correct phase, my state in the Hilbert space is going to be changing in a direction which is always orthogonal to where the state is right now. Any questions or comments about this feature of the Berry phase? We can view this as the criterion that fixes the Berry phase for us, that variations in phi are always orthogonal to phi itself. So here I wrote this here. After dressing with the Berry phase, we have an equation of this type. So this is a less well-known, but maybe more interesting way of talking about the Berry phase. I call it, or people call it, the Berry parallel transport condition. It's the statement that if you want to get the phase right, including the Berry phase, you can just impose this condition at all times and you'll be good to go. So it says that the phase is such that the state always changes orthogonally to itself. Any questions about this? I suppose that this presentation of the Berry phase may be different from what some of you may have seen on other occasions about the Berry phase, or maybe not. So how do we connect this to ADS-CFT? Well, in our problem before, we also had varying Hamiltonians. They were the modular Hamiltonians for the varying regions. So our H's were modular Hamiltonians. They also varied, but they varied with the region. In the Berry problem, they varied with some abstract parameter space lambda. We should just think now of lambda as the space of regions and go ahead and study the Berry phase, where the space of parameters is the space of regions. So, so here is a picture which describes what we will be doing in a pictorial way. This is technically a picture of a fiber bundle, but you don't have to worry about this language. So in the Berry problem, the picture is here to highlight the actual similarity between the two problems, the Berry problem and the ADS-CFT problem we have. On the Berry side, we have some family of ground states, lambda. These ground states are ambiguous by a phase, and so I draw these various phases here in the vertical directions. And then I'm asking, as I vary my ground states over a set of parameters lambda, how does the phase change? And when I make a closed loop in the space of ground state, did the phase change or not? And the change in the phase is the Berry phase. In the ADS-CFT correspondence, we have a set of regions. We will also be making a loop, okay? And then we're asking, these vertical directions now are the labels of coordinates or the local coordinate systems along the RT surface. I'll be making a closed loop and I'll be asking, is the coordinate system near the RT surface the same or different? So it's just like the Berry phase. If I can convince you that the rule for this transport, which is what these arrows are doing, this is the parallel transport rule, is the same as the rule here. Well, the rule here is the modular, not the modular, is the Berry parallel transport. So how do I define a rule for these orthogonal, for these coordinate systems, which is the same as the Berry rule in some sense?
Bartek, so suppose, yes. I think I'm asking a question now, which you will answer later. If not, so this local coordinate system is something that is a property of the bulk. How does it relate to the boundary? Any boundary observable?
Oh, in the boundary, it was the difference between one observable OA and the modular flow version of OA.
But we do not know which coordinate system would relate to which.
Oh, but we don't have to make a. In fact, we only need to treat this relationally, as in, I can say that a change between one coordinate system and another is equivalent to a change between one set of labels and another set of labels. Why? Because on the bulk side, I apply the symmetry, and I know what that symmetry is in the bulk.
Yeah, I understand what you're saying. It's a relational thing, but suppose I'm measuring some particular component of the Riemann curvature in the bulk, right? I would know. So I guess you would say that this new sigma would stand for some specific local coordinate system.
Well, to compute something like R, basically to compute gauge invariant quantities. So like a connection is not gauge invariant, but the Riemann tensor component is gauge invariant. Well,
okay, maybe I should ask this question later. Maybe you should just continue.
Yeah. So basically, if I make closed loops, then I have gauge invariant objects, and that's good. And that's why I'm drawing these closed loops. I think that ambiguities only show up when I start talking about open curves, but for closed loops, it's okay.
No, maybe I will ask it later again here.
Okay. So, okay. So
sorry. If I may just make just a clarification. What you're saying is actually this condition that you're putting psi d psi is equal to 0, which you have slightly higher up. This is this follows from the previous slide that you have, but there actually you have an ambiguity. You can put a total derivative term, which will not contribute to the full loop integral, right? So in that sense, you have more information which gets thrown away when you do the integral. So this is an extra condition that you're putting, isn't it? In other words, what I'm saying is that there is a projector here which throws away anything that could have come if you had a total derivative term there, right?
That's correct. That's right. So if I have a total derivative term, that total derivative term changes what we would mean by a total derivative term is, let me imagine that I have a different set of psi's which differ from my set of psi's by some phases. Now,
yeah. So what I was meaning is that this one form is ambiguous up to a d psi or d of something else term, right? Because the one form is being integrated. If you have a total derivative of some scalar or zero form, that would not contribute to this.
Well, that zero form would be equivalent. That extra total derivative term would be like saying that I'm not going to apply the Schrödinger equation for the individual steps, but I only will say that I get the correct phase after I close a loop. And so I applied the Schrödinger equation in deriving this equation, yes. But you could say that Schrödinger equation is meaningless because it only fixes a phase for me, but the phase is unphysical, so I might as well just go ahead and change phases. Well, in that case, that would be equivalent to adding a total derivative term here, and then this would not be true. So this is a statement about
that I thought would still be true. That term is not going to.
No. So I don't want to. I mean, I don't know how I'm doing on time because
okay, yeah. So this is not very
too
important
much right now. I don't want to sound. I don't want to sound authoritarian, but it is definitely true that if I go ahead and change phases, then this formula would not be true anymore.
Sure. Anyway, you are in China, so you're allowed to be authoritarian.
I even have to be. I mean, that's my indeed. So right, but I'll be happy to discuss this later. So it's really a way of doing gauge theory where I impose some particular condition along the way. And you can think of this condition as trivializing the connection. Okay, because remember the connection is psi dot, yes? Now, if I choose my psi to be phi, to be this solution, then phi d phi is equal to 0. So I'm just giving a condition that trivializes the connection. Maybe that's helpful. So the parallel transport condition is just saying, how would I choose a gauge so that my connection components vanish? Maybe that's an equivalent way of phrasing this. And so here too, I could imagine there is some abstract connection that tells me how I move this coordinate system from one RT surface to another. And if I envision this connection as having components, then I can ask, how would I make those components vanish? And then I will pick those gauges so that they vanish along the way. And that's the meaning of this picture on the right here. Okay, so here is my parallel transport condition, or equivalently, the connection trivializing condition. And the question is, what would that be for the modular problem? Well, what do we have in the modular problem? We also have these Hamiltonians, and then we will vary them with the region lambda. And so here is the answer. I'm just going to pull it out of the hat, and then I will argue that this is the correct answer. By the way, can people hear me or no? Because suddenly I stopped hearing questions, so I'm a little concerned that maybe.
No, now your audio and video is perfect.
Okay, good. So here is an answer which I'm pulling out of a hat. So I have this Hamiltonian H in the CFT, that's the modular Hamiltonian. I will be looking for an operator V such that a commutator with H generates the change in H, plus some terms which may commute with HA or with rho A. And this is a statement that if this H is a generator of boosts that preserve the RT surface, maybe I'm looking for something that will take these boosts and move them to other boosts. That's like a vector field that takes the RT surface to a new RT surface. So that will be the meaning of this equation from the bulk point of view. But in the boundary, it's just this equation. And then I have to impose one further condition. Why? Because as stated, this equation doesn't have a unique solution. It has many solutions. Why? Suppose that I have some V0 which commutes with H. Well, then adding V0 to my V gives me a new V. Yeah, this equation will be unaffected. So I have to fix an ambiguity in V and declare that V has no components that commute with HA. And I claim that this set of conditions is a direct generalization of the Berry phase. So first of all, it's a well-defined definition of how I would vary modular Hamiltonians from place to place in the CFT. So it's a good candidate for my modular parallel transport. But on this slide, I want to ask the question, is it actually a Berry parallel transport? As in, is it just some arbitrary rule, or is it related to the Berry phase? And on the next slide, I will tell you about what it looks like on the bulk, in the bulk. But for now, it's some candidate. And then let me check if that candidate agrees with the Berry connection that we just reviewed a moment ago. Is the plan clear?
Just a question. So this is the same way you could have also phrased the Berry connection in the quantum mechanical, usual quantum mechanical, in terms of the Hamiltonian, right?
Yeah, so I'm just gonna, that's exactly what I'm gonna do right now. And so let me just go through this briefly. So suppose that I apply exactly this formalism without changes to my usual Berry problem. Well, what do I have in the Berry problem? I have a ground state. That means that I have some projector onto the ground state psi, and this is my density matrix rho. That means that the Hamiltonian, if I use this formula, looks like infinity on any space orthogonal to psi, and then some constant on psi. Okay, so the Hamiltonian is just proportional to psi itself, effectively. Now I take this equation v comma h equals dh. There may also be some terms that commute with rho, but there won't be any for reasons that I will not get into right now. But in this case, they just will not arise. So I'm going to take this equation and find a solution. What's the solution? Well, if my rho was equal to psi, then the solution will be d psi minus psi d psi. Okay, but now I have the second condition, which is that V should have no components which commute with my HA. Well, is this automatically satisfied? No, because think about what happens when psi and d psi have some overlap. If psi d psi have some overlap, that means that part of this psi d psi is actually psi. And here I will also have a piece which is psi, but it will have the opposite sign. So this minus will conspire to give me an definite sign addition of psi itself. So that means that I will not, in general, satisfy this condition that V has no components which commute with HA, because if I don't satisfy this condition, then my V will contain a multiple of psi psi, which commutes with H, The only way that I can satisfy this condition, that V has no components that commute with HA, is if I impose from the start that, in fact, this overlap vanishes, as in if I impose my psi d phi condition equals 0. But what is that condition? This is the condition for the Berry parallel transport. And so I see, this is where we recognize that if I follow my nose and actually take this definition of parallel transport and apply it to this very specific case that Berry had in mind, then I produce exactly this condition, which is the condition that Berry found. And so this is the argument why our modular Berry transport, which is defined in this box, why it deserves to be called Berry, because it reduces to Berry's condition for parallel transport when my state rho, my density matrix rho, is a projector onto a ground state. Are there any questions about this argument? Now, let me just pause for questions. So I realized that this slide was a bit quick to actually absorb it, but you can do it at home. Let me just say that here's a set of equations, and I'm considering a very specific case where this rho A is a projector onto a one-dimensional subspace of the Hilbert space, and then finding this V from this box is equivalent to solving this condition. So it really is a generalization of the Berry phase. Okay, I'm gonna assume that you don't necessarily object to this statement. I'll be happy to explain it later, but let's look at what it means in the bulk. Well, in the bulk, we started from these H's, which were representing vector fields which are orthogonal to the RT surface. And we have, let's say, two of them, one for the region A, and then I'm varying in the space of regions. So I'm going to a new region, and now I have a new H, A prime. And in the box on the previous slide, I was supposed to solve these conditions, find some V, which upon commutation with H gives me a variation in H, and then make sure that that V has no terms that commute with H, okay? And because I interpreted in the bulk H's as vector fields, let me interpret V also as a vector field. And so I'm looking for some new vector field eta V from the bulk point of view, such that it satisfies the same equations I have over there, but written in terms of bulk vector fields. And what do those equations mean? They mean that I'm looking for a vector field that maps one minimal surface to another, and it has to satisfy this extra condition that it has no components that commute with rho H. But what are with eta H? But what are the things that commute here? These are those diffeomorphisms that preserve the RT surface. And so the statement is that I want to find an eta V which maps my RT surface to another, but it has no components in the direction that correspond to vector fields that actually are Ryutakainagi surface preserving components. So what are they? Orthogonal boosts and diffeomorphisms that preserve the minimal surface, which are longitudinal. I just need to find a vector field that contains none of those. No orthogonal boost and no longitudinal shifting component. And if I find such a vector field, and there always is one, then that's the bulk representation of my modular Berry parallel transport. Any questions about what I said just now?
So how does it become a pointwise relation? Because suppose I want to do it at a given point in the bulk, is there some specific direction I should take? So my question is as follows. So you're doing some change in the space of regions, and that should map, that specific change should map to a specific point in the bulk, a point on this RT surface. But this identification is rather unclear, right? If I understand.
No. We are not looking for a bulk point. I go from one region to another, and I'm looking for a vector field which is defined in a neighborhood of the RT surface, which will be such that it takes my RT surface to a new RT surface, and it does so without any longitudinal components and without any boost components. But I'm never looking for a vector field at a particular point. It just has to do the entire RT surface. that's the reason why I said that the curvature we will find is not like the Riemann curvature at the point, but it's that like surface-wise combination of various curvatures.
Okay, I see. Thanks. Okay.
So,
Sorry,
so
I have another question. Sorry. Have you used the adiabatic approximation in this setup? I mean, we can.
This is not a dynamical setup. So in the Berry case, we imagined actually taking a knob, and the knob could be moved fast or slow, and the system was evolving. But here we are not. This is not a time-dependent setup. We are going from, there's an abstract. It's an abstract operation going from one region to another, but those regions are in general space like separated. So it's not like I'm going from one region to another and time passes. And so that question is kind of doesn't apply. There is we can talk about what that means for this thing to be slow or fast. Basically, in the context of if I go from one region to another and they are finitely separated from each other, then the question is, did I do it smoothly or did I do some kind of pointwise approximation? Yes. But yeah.
Thanks.
So okay, so I just want to give you two examples of what the modular Berry, and this is the last slide. So I want to give you an example of what this curvature is. Yeah, I mean, well, first of all, what are these like modular Berry phases or generalizations of them that are defined this way? So I just told you that whenever I go from one region to another, I get some vector field, and the question is, when I take a closed loop in in this space of regions, I can take one step along one vector field, another. I come back to where I started in terms of the regions, but what did the vector field generate for me? That's the kind of question. When my loop is infinitesimally small, this is literally the curvature of this modular Berry connection. And so let's look at what it can do. So here is the first situation where I take a region and I move it in one direction, another. And this is kind of a completely generic little rhombus in the space of regions, a completely generic one without any structure. And the kind of picture that it produces is exactly the picture we saw before, which is here. I started from some region, it had an RT surface, and then I moved that RT surface around, and then I compare what the resulting coordinate systems, how they mismatch. Okay, so that's that. And we had an argument to this effect in the paper that I cited, but then in this paper that I was not a co-author of, by Jan de Boer and Lampros, this thing was actually computed. And they have an explicit formula for what this difference between the blue and the red arrows on top is going to be. I don't have a formula explicitly written down for you, but it involves the Riemann, various components of the bulk Riemann curvature tensor, and one extra object. And this is the correction that I mentioned at the beginning of the talk, which is the extrinsic curvature of the surface itself. In 2+1 bulk dimension, an extremal curvature has only, this K identically vanishes because it's a geodesic. It has one extrinsic curvature as one component, so it has to be 0. But in higher dimensions, there are these corrections that have to do with the shape of the minimal surface itself. And so it's some combination of both this guy and that guy. And this is the reason why I titled the talk the way I did. It was a little bit of a provocative title. So the answer is actually not that the Riemann curvature is literally the Berry phase. The Berry phase is that and that in some combination. And TLTW means too long to write. It's some complicated expression. But then it actually has some interesting simple thing that we can write about this, which is whatever this curvature is, it corresponds to some vector field that does something. Okay, I can think of the change in the blue and the red arrow itself as a vector field. And then I can ask, is this vector field a symmetry which has some Noether charge? And so here is the Noether charge of just that symmetry expressed in terms of dx mu, dx nu. Dx mu and dx nu are exactly these changes in the various directions of the of the RT surface itself. And so at least from this picture, you can see that this object really knows about the curvature and the extrinsic curvature in some fashion, which at this level, at the level of the curvature tensor itself, it's complicated. But at the level of what is it another charge of, another charge is actually quite simple. It's this. So that's from that paper. But then I want to tell you that even though we started from the question, what is the dual of the Riemann curvature? In fact, the object we have constructed, the modular Berry curvature, is richer even. And so here is a very special case of region variations that you can do. Take some region in 2+1 bulk dimensions. I'm going to do it all at equal time, so I'm not even drawing time here. And just vary that region as you go around the surface. And remember, I need to think about what kind of sequence of little vector fields would do this, that satisfy the condition. But our condition is that I have no component along the RT surface. That means that when I map one of these geodesics to another, that means that if they intersect, that means that I am just literally rotating about the point of intersection. So let me do this. I rotate in going from one geodesic to another. I rotate about the first intersection point and about the second one and the third one. And I can see that the initial intersection point is just receding further and further away from my current intersection point. So here's a picture this way. Here's a picture this way. What will happen when I form a closed loop? It's going to be to recede by an amount which is equal to this length and this length and this length and this length. It will be equal to the length of this curve. This is exactly what's called the differential entropy formula. And there's some explicit expression for it, which I didn't write down. But that too is a special case of this modular Berry phase, where the regions were varied in this very specific fashion. Now, if you ask what is the curvature in this case, that's a question about an infinitesimal loop. And we can do it this way. I can start from this little geodesic, move to this geodesic, then move to this bigger geodesic, then move to this even bigger geodesic and back to the one where I started. This thing, there are 4 geodesics that I drew here. And so if A and C are small, then this corresponds to an infinitesimal square in the space of regions. Yes, I go from AB to B to BC to ABC and back to AB, that's a square. And that curvature ends up being a translation by the Ryutakainagi entanglement entropies of AB plus BC minus B and minus ABC. This is what's called the conditional mutual information. And so, so that's some very interesting information theoretic quantity. In that case, at least, the modular Berry connection agrees with a quantity that is very salient in quantum information theory. Okay, so I'm going to stop right here. Oh, let me just say that there is another interesting case where you can relate the modular Berry connection to proper time in the bulk, but that story is a little more complicated, and I'm also not a co-author of this, but I invite you to check out this paper where this is explained by Lampros and by Daniel Jeffers. And I'm going to just display this picture, this text here about what I'm thinking about next, thinking beyond, which is about how this relates to holographic complexity. But let me stop here because I'm way over time. Thank you very much for your attention.
Thanks, Bartek, for this wonderful talk. Yeah, so Daniel Jeffries actually gave a talk on this earlier on our thing. Yeah.
Oh, excellent.
Even before the paper came out, I guess, or just after the paper came. No, actually before. Sorry, before the paper came out. Actually. Yeah, so this holographic complexity thing, I think there was also a talk earlier before, which was relating where they found, I think, this TT bar deformation, and that turned out to be like a Euclidean Berry phase indeed, because if you go from A to B and then B to C, it's exactly like going from A to C. The complexity of going from A to B and B to C would be exactly the complexity of going from A to C. Is this something like you mean as so let me tell you, the result that they had was that you take a TT bar.
Who's they?
Okay, it was Heller and Jan Boyer. They had this paper called.
Yeah.
Yeah, so they had this result that if you take 2 TT bar deformation of a CFT ground state, so they are putting 2 cutoffs in the bulk and then they derive this as some path integral optimization. They get some result which is like 1 over z minus 1 over z prime, which is, so
Yeah.
that if you take like you go from A to B and then
I'm very familiar with that paper.
Okay, so is it what you mean in this context, like Berry phase, or you mean something else? Maybe you could just.
Okay, so that paper is written in a way which completely obscures that connection, but in fact, these things are very closely related. And yeah, basically what I'm describing is that result, but in far greater generality. But there are a lot of things that are superficially different in that paper, but they are not essential to that paper. So for example, they don't actually really use the TT bar deformation that much in their argument. When they compute the complexity, they are really just using the bulk calculation, but they're just doing bulk calculations that are not really dependent on the specific realization of the cutoff, whether it's TT bar or not. So that's one statement. Another one is that they are varying the system from one time slice to another. So this is kind of a time-like motion from one state at one time to a state at another time. The thing that I am describing over here is a little bit like a wick rotation of that result, because I'm envisioning actually going from one region to another on a space-like slice, and the regions themselves carve out a region in the bulk, just the way that it's drawn over here. And so you can ask, how can these completely two different interpretations both be correct? And maybe they are both correct, or maybe only one of them is correct, and mine might be wrong, and theirs might be right. But at the level at which they have done this, their results are essentially fixed by the symmetry of by the conformal symmetry. They are working in pure ADS3 as far as I remember. And so symmetry in that case is so powerful that it can make both their interpretation and my interpretation correct at the same time. And so here are just some of the comments on the scattered comments.
And sorry, my question was that if the result is that you take one of this TT bar deformed state to another, say A to B and then B to C, and that would be the same as going from A to C. So it would mean in your language, the Berry curvature is 0 probably. I don't know. I mean, does it ring a bell, or is it, there seem to be the results seem to be like that. So how would you explain that in your?
They are effectively looking for, I mean, again, this is not phrased in that way, but they're effectively looking for, so we have a connection here, yes? So now you can ask, is there it turns, we don't need a metric to define a geodesic. We just need, like if we write down a geodesic equation, only the connection shows up, but the metric does not. And so the moment we have a connection, we can talk about about geodesics. And they are basically following lines, geodesic lines. These are not geodesics in the bulk. They are geodesics in the sense of being straight lines with respect to the connection that we have defined in this talk. It's a connection in the space, in kinematic space, in the space of regions. And so they're basically following geodesics. Now, when you follow a geodesic, then it's true that you can go forward and backwards, and you're not seeing any changes because, well, okay, because you're really moving on a straight line. So there is that. They are solving certain equations of motion in there to make that, before they make the statement you're referring to, and those equations of motion effectively amount to finding geodesics with respect to the metric, not with respect to the metric, with respect to the connection that I discussed here. Yeah, so that's another
case of geodesic. Isn't it surprising that normally the length from A to B and length from B to C is not equal to the length from A to C, right?
Well, if you follow a geodesic, then if they are collinear, then yes. And so what I'm trying to say is that they're basically working in a collinear case in some sense.
Okay.
Collinear in the space, in kinematic space.
Okay, they're somehow defining some way, some metric in which
it's very But they're not. But they're not defining a metric. What I'm saying is, so
okay.
actually in this, so in this work in progress, which I am signaling here, we are actually defining a metric. But they're not doing this. But what I'm saying is that the equations of motion are secretly equivalent to the metric equations that will show up out of this work. And in fact, notice that Jan de Boer is a collaborator on both that paper and on this paper. So there are not going to be conflicts. There's just going to be a greater cohesion when we eventually sort out this story.
Okay, so maybe
but there are let me just say that there are a lot of superficial differences between that paper and the work in progress that I'm describing here. But in fact, it all fits nicely together.
Okay, so I think one of the authors of that paper is also in the audience, Mario Flores. Okay, but
Mario, hi.
So,
if Mario wants to comment on this, I'll be happy to take the heat. But I don't think that I mischaracterized the paper in any way. And I'm also saying that I'm actually agreeing with everything that's in there.
Okay, so
okay, many thanks. I don't have any comments at this point. I also need to go through your work in more detail to understand it better. But thanks for the kind words about this.
Thank you, Mario. No, and thank you for coming to the talk. I appreciate that.
Thanks.
So is there any further question that we can ask Bartek? Maybe we can take a couple before we end. Sorry, I asked the first question. I shouldn't have done that, but I was very curious to know about this complexity story.
Sure.
Okay, so I apologize again for asking the first question. Maybe it's already.
Thank you for the question.
Okay, so thanks Bartek again, and it's good to have you, and hope we can have you again, and you will visit us in Chennai at some point. And
I would love that, and I'm counting that. Well, I don't know how many days it will be, but I'm really looking forward to the time when international travel is possible again, and let's visit each other profusely.
Yeah, sure. Okay. So on that note, let us end today's session, and the next one would be on Thursday next week. It would be on M-theory, new paper on this M-theory realization of topological phases of matter. Okay, so good. So have a nice evening and rest of the day. So see you all in a week. Bye.
Thank you so much, and good night. Thank you.